So this video will cover the most likely scenario that you encounter when solving equilibrium problems, and that is that you'll be asked to solve for the equilibrium concentrations. You will know the equilibrium constant, and you will know something about the initial conditions. So the first thing that I want to give you are the specific steps that you should follow. Now they're going to be really similar to what we did in the earlier video in solving for the equilibrium constant, but obviously adjusted a little bit because we'll know the equilibrium constant in this case. And then we're going to do two examples. So, step one, not surprising, but fill in the stuff that you're given, that you know, which is the initial conditions in the ICE table. Well, the RICE table, as we're calling them this semester. Second, calculate Q to determine the direction of the reaction. Now, if you can determine the direction of the reaction without calculating Q, right? Remember those cases where you have zero reactant or zero product. You don't have to do a calculation, but you need to pause and consider which way your reaction would go. Then you will fill in the change row. Now, when we get to this, and you'll see in the two examples, we won't have a number, right? We don't know how far it needs to go to the right or the left to get to equilibrium conditions. So you will fill this in with values of X that match the stoichiometry of the reaction. Then complete the equilibrium row. Then you will substitute values from the equilibrium row into the equilibrium constant expression. And what you will be left with at this point is an algebraic equation that you can solve. So you will solve for X and sub the numerical value for X back into the equilibrium row to get your equilibrium concentrations or pressures. Okay, so these 6 steps, we're going to use these to do these 2 example problems. I strongly recommend keeping these steps up as you're doing practice problems until you feel really good about taking a problem, analyzing what you need to find and where everything needs to go, and then solving for it. So our first example will be a little bit generic. So we are asked to find the concentration of A and the concentration of B at equilibrium if the initial concentration of A equals 1.0 molar and the Kc is equal to 0.33. And we need a balanced reaction in order to do this. So I'm going to get my RICE table set up. And the generic reaction that we're going to use here is A in equilibrium with 2B. So the things that I know, so the initial conditions for the ICE table, based on what's given in the problem, is that the initial concentration of A is 1.0, and I'm not given any information about B. So it starts out at 0. If I have no product, my reaction must move to the right. And what that means, without worrying about the x's or the stoichiometry, is that I'm going to use up reactants. So I'll subtract from the reactant side, and I'm going to add product. So I'm going to need a plus sign on this side. Now, based on the stoichiometry, what's kind of nice about this is that you can just carry down the coefficients, right? So whatever it is, I'm going to lose 1x because my A has this coefficient of 1. I'm going to make 2b, right? Because 1a turns into 2b. So that's exactly what is going to happen in my change row. And now my equilibrium row, when I add these together, the concentration of A at equilibrium is 1 minus x, and the concentration of B at equilibrium is 2x. Now, my equilibrium constant expression looks like the concentration of B squared over the concentration of A. So when I substitute this in, I need Kc equals, B is 2x. So that entire 2x has to go inside the parentheses to B squared. And then in the bottom, I have 1 minus x. And I know the value for this. I know that this equals 0.33. So I have an algebraic equation that I'm capable of solving. So this is obviously going to take us a little bit to get through, but this is algebra that you know how to do, and you should practice this a lot if you feel like you need a refresher. So I'm going to go ahead and expand my 2x squared, right? And it's 4x squared. This is one of the most common mistakes, is forgetting to square that 2. So just be really conscientious when you put your stuff in here. That's all over 1 minus x, and it equals 0.33. So I'll throw this over 1 in case it makes it easier for you to see the cross multiplication. So I need to cross multiply here. So 4x squared equals 0.33 times 1 minus x. And I'm going to expand this over here. 4x squared equals, don't forget to distribute that 0.33 all the way through the parentheses. And then, this is not necessarily something that you can figure out on your own, but if we rearrange it a little bit, say if I make it, say, 4x squared plus 0.33x minus 0.33 equals 0. This is something that you can solve with the quadratic formula. And I'm very sad to not hear you all groan in class, since this is now a video lecture. But if you need a reminder, first of all, it's on the equation sheet. I'm not asking you to rememorize this, so you can look it up whenever you need it. But remember, it's minus b plus or minus the square root of b squared minus 4ac all over 2a. And that plus or minus bit, right? This is this quadratic formula, the x squared, means that you get 2 answers out of it. So that is going to cause us a bit of an issue. So I get 0.2489, and I get negative 0.33. In this case, one of these answers will be very obviously wrong. In some cases, you may need to plug these back into the equilibrium row to figure out which one is wrong. Now, if you get a negative value, you can almost always reject that automatically because it means it would try to make the reaction move in the opposite direction that you have already predicted. Now, if we look back at our equilibrium row, right, at equilibrium, the concentration of B is 2 times X. If I did this, I would get a negative concentration. So I will reject this value, this answer, based on that. So we reject because it gives a negative concentration, which means my actual answer is 0.2489, but that is not the answer to my problem. This is just the value for X that I have solved for. I still need to go plug it into the equilibrium row to find my equilibrium concentrations, right? At equilibrium, A is 1 minus X, so 1 minus 0.2489, and the concentration of B is 2 times X, so 2 times 0.2489. So at equilibrium, my concentration of A is 0.7511 molar, and my concentration of B is 0.498 molar. And these are my actual answers at equilibrium. So one more example using these steps to solve a problem, and this one will be a little bit more explicit. So our reaction, which just to save some space, I'm going to place it in the ice table. So the reaction N2O4 gas in equilibrium with 2NO2 gas. The Kc for this reaction equals 0.36 at 100 degrees Celsius. The initial concentration of NO2 is 1 molar, and the initial concentration of N2O4 equals 0.1 molar, and we need to find the concentrations of both at equilibrium. Okay, so rice table, initial conditions, N2O4 is 0.1, NO2 is 1.0. It's not obvious which direction this needs to move. It might be a little bit clear, I mean, looking at how small the equilibrium constant is, but let's properly check this. So my Q value is 1 squared divided by 0.1, which is 10. So Q is definitely greater than K, and that little greater than sign is kind of marching to the left. So my reaction needs to move to the left. So my balance of product over reactant is product heavy, and according to my equilibrium constant, which is less than 1, it should be reactant heavy. So if my reaction is moving to the left, I'm going to make reactant and lose product. Based on the stoichiometry of the reaction, I will lose 2x and make x So at equilibrium, the N2O4 concentration is 0.1 plus X, and the NO2 concentration is 1.0 minus 2X. All of this will get substituted into my equilibrium constant expression. So in the top, it's going to be 1 minus 2x squared. In the bottom, 0.1 plus x equals 0.36. Go ahead, throw this over one so it's easy to see the cross multiplication. So we're really getting into the algebra for this one. I'm going to cross multiply. I won't distribute anything, but I'm going to write this 1 minus 2x out twice as a reminder that you have to properly expand this or you will not get the right answer, right? This does not expand to 1 plus 4x squared. You have to distribute the 1 and distribute the minus 2x through the entire parentheses after it. There are techniques that can help you. If this is something that you struggle with, please ask me and I can point you in a direction that has some good resources. So if I expand this, what I have is 1 minus 2x minus 2x plus 4x squared equals 0.036 plus 0.36x. If I combine these terms and get everything rearranged, this turns into 4x squared minus 4.36x plus 0.964 equals 0. So not something that I can get through very easily, but something I can plug into quadratic formula. So for this one, I will go ahead and substitute these numbers in to make sure you feel like you're on the right page when it comes to substituting these values, right? So in terms of A, B, and C, right? 4 is A. This minus 4.36 is B. And the 0.964 is C. So X equals the opposite of B, so plus 4.36 plus or minus the square root B squared, so negative 4.36 squared minus 4 times A, which is also 4, times C, which is 0.964. Square root of that whole thing. All of it divided by 2A, so all of it divided by 8. When you get the two answers out of this, one of them is 0.7817 and the other is 0.3083. So neither one is negative. We don't have a really obvious one to reject here. So in order to find one to reject, we have to look at the equilibrium row. And I think one of the easiest ones to look at is the 1 minus 2x, right? So this NO2 concentration, 1 minus 2x equals, if I plug in this 0.7817 for x, 2 times 0.78 is going to be bigger than 1. So this gives a negative. and 2 times 0.3083 is less than 1, so this one would give a positive. So we can reject the 0.7 because when it's plugged in, it would give us a negative concentration. So reject the 0.78. So x equals 0.3083. Again, still not my actual final answer. I need to plug this fully into the equilibrium row. So my N2O4 concentration is going to be 0.1 plus x, 0.3083. So 0.4083 molar. And my NO2 concentration is 1 minus 2 times 0.3083. And that value is 0.3834 molar. So these are my concentrations at equilibrium.